Hey, and welcome to our presentation for Economics 3374. My name is Faraz. Alongside Gabe and Kirby, we've put together over the past week this presentation for you on the paper titled Climate Change, the Ultimate Challenge for Economics, written by William D. Nordhaus. Starting off with the introduction, the purpose of this paper, Nordhaus wants to subject the externalities of economic growth, namely and obviously with a special consideration on climate change and the effects of that. So to do this, he reconciles climate change modeling with the economics of technological change, and it turns out when you do this, they both manifest a public good, which can be regarded as an externality, and they both show an inability currently to efficiently allocate the resources necessary to combat climate change. So the point he makes sort of at the end of the conclusion is that, look, technology took us out of the Stone Age, which was great, but if it failed to do anything about climate change, it's going to threaten to take us back. First point that Nordhaus makes regards climate change as a global public good. Turns out global public good can be regarded as an externality, as I mentioned before, and climate change is the most significant negative externality, which he sort of signifies in this image, showing this colossal titan to represent the magnitude of the problem that we're dealing with and have at hand. There are positive and negative externalities, positive ones like knowledge, negative ones like pollution, which is the obvious focus of this paper. It turns out externalities on a global scale are very difficult to treat, and this is because they resist the control of governments and majority markets, which are generally domestically concerned. So climate change being a global good or global externality means that the entire world needs to be on board in order to tackle it with results. And just what's even worse about that is that there's a lack of legal enforcement now, and there's little incentive to follow procedures, whether that be on a national or on a citizen basis. To follow procedures, since global involvement means that there's going to be minimal or less benefit per individual, whether you want to regard that as an individual or as a country. And so there's less incentive to really tackle and do what is necessary. Getting into the technicals of the paper, Nordhaus talks about an integrated assessment model. And what they basically are is they link several disciplines, usually more than two, disciplines together to develop an actual effective understanding of whatever the concern at hand is. And after many iterations, Nordhaus developed, which is shorthand for IAM by the way, he developed an IAM model that hit on all parts of the dynamic integrated model of climate and the economy, which is shorthanded to DICE. And these are based on scientific theories and computational models, so it's a fairly objective consideration. So as you can see, there's a logical loop of emissions that he outlines here. So the global warming problem starts here on the top left. So economic growth leads to CO2 emissions that results to a rising CO2 concentration in the atmosphere and other forces which lead to climate change. Then climate change imposes ecological and economic impacts. From there to the bottom left now, the climate change policies should be in place to reduce the emissions, and then it goes back up again because economies continue to grow. Now notice in the first two arrows, they're outlined, and then the final two arrows, they have a question mark in them, and what that means is that link currently does not exist. Now this is quite a pessimistic realization, but this really does highlight the importance of the problem. And so this is very interesting. He goes and produces a mathematical representation. So what you see here, you can take pause and take a look at that, but outlining the variables here. Now we're looking to max welfare, as we discussed in class even. So C of time is the consumption, Y of time is the endogenous variables, Z of time is the exogenous variables. So alpha is going to be just some parameter, and P is the rate of time for reference, which is presumably constant. And then the epsilon at the end is of random variables. Not just to pull up some examples of what the endogenous and exogenous variables might be. Endogenous variables are going to be stuff like global temperature, and exogenous variables are going to be things like population. Nordhaus goes in to talk about the evolving science of climate change, and he starts off by making an analogy to a casino that is a current problem we have right now. So he says climate change hitherto is a vast casino that we can exit. And what he means by this is that climate change produces a variety of unexpected and dangerous changes in the world, and we just need not roll these dice and walk out of this hypothetical casino while we still can. So there are a variety of changes that he goes through about how our Earth has responded to climate change. And importantly to note, the CO2 concentration has nearly doubled in the past 250 years in the atmosphere, and it's going to double again within the next 100 years with our current rates. And so that's quite astonishing to recognize, and it's sort of represented here in this chart. This chart ranges from 2% to about minus 5%, and it's showing the global temperature variations based on the Antarctic ice core data. And so the Antarctic ice core is very rich in the data that it can produce, and it's extremely reliable. But as you can see, it sort of fluctuates, as I said, between 2 and what looks to be -5 degrees. And all those dips, when it gets down to -5, have been historically ice age periods. And it follows quite a concise pattern. And we're working with about 400,000 years of data here. So seeing at the very right, which is the projected rate with our current emissions, it goes quite out of the pattern of the quite out of the pattern in that little box that we've historically had. And so the proposition that this is going to be a natural phenomenon and that our emissions aren't going to have that much of an impact is quite unreliable in the face of this data. So Nordhaus goes on to talk about the things that we can do to slow climate change now, and he outlines 3 strategies that other economists have produced hitherto. Plan A being abatement, which is simply reducing our carbon emissions. Plan B being carbon removal, is just simply taking out carbon dioxide from the atmosphere to combat what we put in. And Plan C, geoengineering. The type of engineering we'd be doing here is increasing the reflexivity of the Earth, such that the sun rays that hit it, most of it are bounced off, and this in theory would reduce the global temperature. And Nordhaus sort of tackles these in reverse, and he says Plan C, well, it's dangerous and untested, meaning that we don't actually know the results of what can be done with this, and it's quite a dangerous thing to be, geoengineering, playing with the mechanics of our Earth, essentially. Plan B, he admits to the attractiveness of this strategy, but it's not feasible, he suggests, with our current technology, our research and development. So all we're left with is Plan A. And the thing about Plan A is that it's very expensive, and this is what's represented in the chart here. So if we want to target a 50% reduction, looking at the left set of bar graphs, different IAM calculations, and you can see the DICE one in there in gray, calculate an average of 1% of global output in order to achieve a 50% reduction in CO2 emissions. So the y-axis, these percentages are in terms of global output. So 1% of global output is quite significant. And conversely, if we wanted to attain 100% reduction in our CO2 emissions, it averages actually 3.5% of total output. So these are quite important numbers.
Damages of climate change. Step 1. Climate change is not reversed. And this is the course that is currently being followed, and as we'll see in upcoming slides, there are many models that predict what the future will look like. A famous quote from Keynes was that it's better to be vaguely right than precisely wrong. That's what these models are aiming to achieve as a minimum. Step 2. The impact of climate change is that temperatures will rise. So what does that mean for our climate? Well, eventually there will be a tipping point. The rapid melting of large ice sheets and large-scale change to ocean circulation, such as the Gulf Stream. This will have huge impact on coastal communities. The image on the right is a worst-case scenario of what New York could look like in the future. And then finally, step 3. Our natural ecosystems will be impacted. Many sectors of high-income countries, such as laboratory clean rooms, are highly managed, and this feature will allow these sectors to adapt to climate change at relatively low cost for at least a few decades. However, many human and natural systems are unmanaged or unmanageable and are highly vulnerable to climate-sensitive physical systems. Low-income and tropical regions like Africa in particular will be heavily impacted. Rain-fed agriculture, seasonal snow, coastal communities impacted by sea level rise, river runoffs, and natural ecosystems will have potential for serious impacts in these areas and irreversible changes. What is the objective of climate change policy? Earlier in the presentation, we reviewed the image on the right and what climate change looks like in the image. However, what is the objective of this actual policy? We often talk about limiting temperature rises. However, it's not that straightforward. The temperature target may be an aspirational goal, but the target approach is questionable because it ignores the cost of attaining these goals. If, for example, attaining the 1.5 degree goal would require deep reductions in living standards in poor nations, then the policy would be equivalent of burning down the village to save it. As well, if attaining the low temperature path turns out to be easy, then of course we should aim for it. These points lead to an approach known as cost-benefit analysis, and it's what dictates upcoming policies that we're going to review. So how do we measure the cost-benefit? One way is to use the integrated assessment model, also known as IAM for short. There are two main features of IAM. The first is that it's internally consistent. This means that the model keeps track of the different stocks and flows of all variables so nothing gets lost. For example, carbon stocks tomorrow are carbon stocks today plus any flows from emissions. Second is that it allows for alternative assumptions. If someone doesn't like the output assumption or the discounting, or wants to pursue a different policy, these differences can be incorporated while ensuring that all other parts of the model are consistent with the change assumption. There are also four overall findings from all IAMs. First off, is that policies to slow emissions should be introduced as soon as possible. Next is that there's a uniformity of price. This means that the most effective policies are ones that equalize the incremental or marginal cost of reducing emissions. Next is that effective policies should have the highest possible participation. That is, the maximum number of countries and sectors should be on board as soon as possible. And lastly, is that the policy ramps up over time. This gives people time to adapt to a high carbon price world and to tighten the screws increasingly on carbon emissions. The image on the right of the slide here shows an IAM as an example. So first off, there's the GDP and population, which are the key assumptions to drive the model. Next, the larger economy tends to use more energy because of these assumptions that we took in the first step. And third is what happens in that. So these changes affect prices as well as the future energy mix, level of deforestation, and amount of warming. So this is just a basic example of what an IAM can look like. And in the next slide, we'll dive deeper into examining this further. A good IAM example is the DICE model. So these simulations estimated the temperature trajectories for 6 sets of cases. No policy, a cost-benefit optimum with standard damages and alternate set of damages, and then 3 additional temperature-limited strategies where the temperature rise limit was 2 degrees. So what were the conclusions? Well, the base path, which is basically the path that we're following now, continues to have rising temperature passing 4 degrees by 2100. In the DICE model, it is essentially infeasible to attain the stringent temperature target of 1.5 degrees, and even the 2-degree path requires negative emissions in the near term. Another finding is that the cost-benefit optimum rises to over 3 degrees in 2100, much higher than the international policy targets. So even with the much more pessimistic alternate damage function, the temperature path rises to 3 degrees in 2100. And one more additional and crucial factor is discounting. So discounting involves 2 related concepts that change the outcome from any model drastically. So the first concept is the discount rate on goods, which is a measure of the relative price of goods at different points of time today and in the future. The second important discount concept involves the welfare of different households or generations over time, and it's called the generational discount rate. It's important to understand and remember these discount rates, as the model will be drastically impacted by what is selected for that discount rate and will impact the results.
Well, thanks, Gabe. I'm Kirby, and I'll take us to the end of our video. The next thing that Nordhaus explores is, well, how are we doing on a carbon price per each ton of CO2? The DICE model would suggest about $36, but today we're at less than 10% of that, even collective of all the policies that the nations have put in place. And in fact, we probably need to be somewhere between $100 and $200 to limit temperatures. So we're nowhere. And why is that? Well, he identifies free riding, consuming a public good without contributing, as the biggest factor. This is not new to international agreements. NATO, for example, many member countries enjoying a collective defense membership, but not paying their full dues into the cost of it, and the US ends up picking up the bill at the end. So this is not new to international agreements, but it's a major inhibitor on global climate progress. And he identifies 2 types of free riding. National free riding, and America First, when Trump pulled out of the Paris Accord, is a good example, and generational free riding. You know, the costs of abatement are now, it's us, it's our generation and the next generation. The benefits come in future generations. So Nordhaus then outlines the history of international climate agreements. So starting with the Framework Convention on Climate Change in 1994, it did recognize the risks of global warming. It did seek to stabilize CO2 levels, but it really didn't have any teeth. And so it didn't go anywhere. A few years later, in 1997, the developed countries gathered together in Japan for the Kyoto Protocol. Now there they agreed to try to keep emission levels about 5% below 1990 levels for 2008 to 2012. And they did propose a cap and trade system, but they didn't really implement one. Now the problem with this one is that the developing countries like China, growing very fast in that time frame and polluting quite heavily in that time frame, weren't even part of the protocol. So the US left quite quickly and it fell apart after that. Fast forward now to 2015, and we have the Paris Accord. The countries at that accord targeted to keep global temperatures 2 degrees above pre-industrial levels. US and China did make significant commitments in that agreement, but still voluntary. No penalties on non-compliance, no penalties for non-membership. So Nordhaus then explores, are these climate policies having any effect? To do that, he looks at a metric called carbon intensity, which is the trend in the ratio of CO2 emissions to GDP. And you can see that it has been trending down for the last 5 decades. That's good, that's going in the right direction. But it's only dropping about 1.6 percentage points per year. And there's been no significant acceleration after Framework and Kyoto. There's the Framework Agreement, and there's the Kyoto Agreement. There's no significant drop-off in the slope of that line to accelerate that metric. And if we look at where Paris is in 2015, well, that you could say, well, that looks like it's having some effect, and maybe it is. But he dissects that, though, and says that China is actually driving most of that. They've cleaned up their act. They're doing quite a bit better than they were in previous decades. And so they've really accelerated. But the rest of the world, still trundling along at about 1.8% per year. The issue, we need to be closer to 2.4% per year to slow global warming. So Nordhaus suggests that the way to get around and overcome free riding is to form a climate club. So just like any club, it'll be a voluntary group that shares costs and derives benefits that are greater than those costs or dues for being part of the club. And that could work quite well if non-members can be penalized and kind of coerced to join the club, and if the membership is quite stable. In that situation, we can get many countries cycling in the same direction on this issue, which would be good. Now, to apply it to climate change, he says the first thing that club would do is form an international carbon price, and they would all agree to adhere to it. And non-participant countries, they would face penalties in the form of export tariffs. If they're not part of the climate club, then when they try to export goods into a member nation, they would face export tariffs. And so for them, it's going to be a question of whether the costs of abatement and living with that CO2 price are less than the costs of the penalties they'll face. If they are, they'll join the climate club. Well, how would you go about setting those carbon prices and penalties? Well, if you're trying to achieve aggressive CO2 reduction, you're going to need a high CO2 price. And that means you're going to have pretty high abatement costs trying to avoid those CO2 prices. And it also means you're going to need high tariff penalties to coerce the non-member countries into joining. So some examples here kind of lays out the issue. This graph is showing the target carbon price that you might go after along the x-axis, and then the average carbon price you're going to achieve with various sets of penalties. So if you're targeting $12.50 per ton of CO2, that's a pretty low target. That's not going to be very expensive to do in terms of abatement, and so you're probably going to need any tariff over 0% is probably going to get it done for you. But if you're targeting $25 per ton of CO2, well, now you're going to need a tariff that's greater than 2% for sure to coerce countries into joining. If you're targeting $50 per ton of CO2, well, now you're probably going to need to be greater than 4% on your tariffs to get anywhere close to that 50 target. And there are declining economies here. If you push the concept too far and you go after, say, $100 per ton of CO2, well, now you can see that even a 10% tariff probably won't be enough to get member countries to join, and you probably still won't get to your target of 100. You'll be lucky to get to 50. So Nordhaus concludes that the $50 target on CO2 per ton or dollars per ton for CO2 is probably about the right sweet spot with the set of penalties that you would probably need to implement. So he concludes the paper with 4 next steps. Knowledge enhancement. Individuals keep learning, keep being involved in this process. Scientific research has to continue. Nations, put a price on CO2, and we've seen Canada do that to some degree the last couple of years with its policies. And number 3, transition from those national CO2 prices to a global CO2 price by forming a climate club and get penalties in place that can be wielded against non-members. And then 4th, develop low carbon technologies. We're going to need those alternative technologies. The government needs to support the development of those and the adoption by consumers. So we have 2 questions for the class this week. The first one just lays out those 4 next steps that I just covered in the previous slide. They sound simple enough, they sound pretty straightforward, certainly logical, but what do you think will be the biggest challenges and obstacles in executing those steps? And you can keep it general and do all 4, or you can drill down and pick one and go into a lot more detail about one of them. But what are the challenges and obstacles? And then question 2, for each of the obstacles that you identified in question 1, what do you think would be a good corrective action that would at least mitigate that obstacle to some degree? And there may be some examples from around the globe that you can pull into your answers. So those are the questions that we have for the class this week. Thank you for watching our video, and we'll see you in Packback.